Nikhil, and then thank you organizers for having me here. As Nikhil said, my name is Ashok. I come from Indian Institute of Space Science and Technology in Trivandrum. So it is an institute under Department of Space or ISRO. So what the topic assigned to me today is quantum sensing. In the background you see our beautiful campus in Trivandrum. If you are in Trivandrum, you may want to visit this campus. So it's really beautiful. So okay, so what I want to tell you that since the topic that assigned was quantum sensing, and then I want to stress here that quantum sensing is really a vast subject. It won't be possible to cover all the aspects of sensing in next let's say 1 hour or 45 to 50 minutes. So what I have rather chosen, I made it little specialized because this is what I do. I work on quantum enhanced sensing with squeeze light. This is the subtopic I'll talk about today. It's like quantum enhanced sensing with squeeze light. So what I'll be talking, what I understood from the organizers, that this conference is for undergraduate students and many of the students which are not from quantum background, or rather not from physics background. So therefore I have made it very simple. Though it is technical, this is a quantum enhanced sensing, or if anything quantum you want to do, it has to be little technical. But at the same time, I have tried to make it little more, easier to understand. So before I go to actual content of my talk, of course, we have very strong quantum technology group at IIST, and here are many of the faculty members in our group. They are working in many aspects of theoretical quantum optics or quantum information. But I would like to, bring to your attention to this lab, the Quantum Optical Technology Lab we have recently developed at IIST Trivandrum. This is one of the state-of-art lab in India that works on quantum squeeze light and entangled light beams. So we are generating some quantum states of light, or some form of quantumness in light that is called squeeze light. I'll tell you about this. Or then they are also entangled light beams. And then, of course, we are not only generating this kind of light beams or quantum light beams at our lab, we are using that for quantum cryptography and quantum communication application. In particular, for the quantum communication, we are part of National Quantum Mission under Department of Space. So Department of Space is planning to have some quantum communication schemes and all. We are part of that. And then whatever goes to the theme of today's talk, that is on quantum sensing and quantum metrology. Of course, we do the quantum sensing and metrology as well as imaging in this lab. That I'll highlight what we have been doing. So one thing I must tell you, that we are a kind of research institute at the Indian Institute of Space Science and Technology at Trivandrum. But at the same time, other than research, we have very strong academic program. Or primarily, I would say that we are an academic institute having like teaching as well as research focus. And then toward the quantum technology as well as since there are so many undergraduate students in this meeting, I would like to highlight your attention that since 2022 we have started an MTech quantum technology program, which is one of the first programs in India in quantum technologies. So it's a successful program. If you want to explore further, you can look at our website. So other than this MTech quantum technology program, we have dedicated undergraduate programs. So we have BTech in aerospace engineering, avionics, computer science, dual degree, and many more, along with MTech and PhD and postdoc disciplines. So with this, I would like to highlight, what is actual motivation. What we said, our lab, we are generating quantum squeeze light or quantum entangled light. So once we are generating these kind of states of quantum light, what we do, or what are the potential actually, that's what you should know. And then here again, I will start with what is theme for today's talk, that is quantum sensing. The light that we are generating, we call a squeeze light. It has a lot of application in sensing and metrology. So if you are aware, about gravitational wave detection, this is one of the most, I would say, one of the largest experiments in 21st century that led to the discovery of gravitational wave. Now, the kind of, this kind of sensitive experiment, they are working at their limit, or they are working at their classical limit. And then if you want to get further enhancement or in the sensitivity of those kind of experimental gravitational wave, then you have to go quantum. And then one of the way to go quantum is, people are trying to interface the quantum states of light, or in particular squeezed state of light, to this kind of sensors to get the sensitivity beyond the classical limit. So for example, this is the black trace was, the sensitivity means what is the smallest change in the, what is the phase shift you can detect. So this was with the classical, and this was with the squeeze light. They could detect smaller changes in the gravitational wave when we interface the squeeze light with our sensing, our gravitational wave detector. On the other hand, this kind of light, squeeze light, has a lot of application for quantum computation. This is a little older work from Chinese group, where they are showing the quantum advantages using the squeeze lights for computational. So this is one of the very, again, leading area where the squeeze light could be potentially useful. On the other hand, for communication and cryptography, squeeze light is also considered a potential candidate. Along this line, yes. Oh, is it? That's, I see. Uh, let me share it again. Do you now you see my slide? At IIST, where we are working on different domains of quantum technologies, and at the same time, I was talking about different programs we have at IIST. This is a little bit about IIST and the quantum research what we are doing here, and then I came to this slide that is talking about the motivation. And then, of course, I said, the kind of state or the quantum light we generate that has application in most of the verticals of quantum technology, in particular sensing, computation, as well as cryptography. And this part I have already talked about. And then what I was highlighting, this green one is the sensitivity they have obtained with the squeeze light or quantum light. On the other hand, in this one, people are working or using this quantum squeeze light for quantum computation advantage also. And then I was here in this part that, it's not only sensing and computation, it has a lot of potential for quantum cryptography or quantum information encoding. So for example, in this work, I would like to highlight that, we have used this two-mode entangled light. This is a work done in collaboration with the University of Oklahoma in USA, where we have shown that you can encode information securely, quantum securely, in those beams. This kind of studies are going in our research group. So with this, what I would like to tell you that what is the focus, that is quantum enhanced sensing with squeeze light, or in particular here also I would like to give a background, because otherwise it looks like a kind of abstract. What do we mean by quantum enhanced sensing with the squeeze light? So I would like to give a background to you that when we talk about sensing, we want to detect a signal which is buried inside the classical noise, which is not possible with the classical tools because it is buried under the classical noise. Then we have to understand what do we mean by classical noise and how do I differentiate with the quantum noise. I would give a simple example. For example, if you have a laser beam, and then if you want to look at the noise, or if you want to detect the noise of laser beam, then what do? You send laser beam to a detector, and then of course detector detects laser light, is intensity or phase, whatever you want to detect. Based on that, you have to change your detection scheme, but ultimately you can see is phase and amplitude noise. And then you use amplifier, and then with the spectrum analyzer, you analyze what are the noise frequencies present in the detector. On the one hand, in the spectrum analyzer itself, we'll have certain background noise or electronic noise. So if you just switch off this laser, if you switch off the laser, your spectrum analyzer that gives, let's say, noise versus different frequency, what noise have at what frequency, you will have a, let's say, electronic noise or background noise. Now, of course, electron spectrum analyzer also can pick up some noise from the neighboring lab, or some, let's say there's some other instrument, then this is like, this works as an antenna and it can pick up some other noise. This is not the noise from the laser. This is a technical noise. This is a classical pickup noise because it is coming from some of the other technical sources. Now when you switch on the laser, what can happen is the whole background, the whole background gets increased. And then, of course, your laser may have some signal of your interest. Then it may show you a signal as well as a background noise. And this background noise is quantum noise. If you have an ideal laser means there is no classical intensive fluctuation, or your DC power supply, or there's no flickering from anywhere. The classical means there will be again certain noise background. That's called quantum noise. On the other hand, your signal, your detector that is picking some noise from somewhere, that is your technical noise. Now, interestingly, this technical noise, if I have a technical noise or classical noise, that can be suppressed out, or you can cancel that noise. To cancel this kind of noise, you can simply make a balanced detection. You just split a laser beam into two parts by a device called beam splitter. You split that into two parts, and then what happens in that splitting, this technical noise that you have can be split out. And then if you do difference measurement, since it is going 50% here, 50% here, then the difference noise, you can cancel out this noise. But interestingly, I want to stress the fact that the quantum noise, which is the background noise in your laser beam, that you cannot eliminate by this kind of technical tricks. So that's the way you have to take home, that if you have a quantum noise, then the classical tricks like the passive measurement that you do after your laser will not get rid of this kind of classical noise. Then this kind of quantum noise. Then the question comes, is there a way to reduce this noise floor? Is there a way to reduce this quantum noise beyond what I'm getting from the laser? So the answer to this question is yes. There's a way to reduce the noise of your system beyond what you get from the classical laser. And the solution or the answer for this is you go squeeze light. If you have squeeze light can have noise less than what is possible with the laser beam. Now, how do we understand that? To understand that, you can go little quantum. I'll not say much quantum here, or like a quantum mechanics, but I will borrow like what we know in our just any elementary book, optics book, that your electric field or EM theory book, electric field can be written as a sine and cosine component, right? Electric field can be written as a sine and cosine component. But if you go quantum, in the quantum mechanics, we treat electric field as an operator. And if we treat them as operator, then you can see that what comes with sine is also some operator. What comes with the cosine also some operator. Ultimately, this is a field, sine and cosine part of the field. But interesting part of these, whatever the operator are coming with the cosine and sine, they are like position and momentum. If everybody is aware of Heisenberg uncertainty principle. When we talk about Heisenberg uncertainty principle, we talk about the position and momentum degree of freedom. So the component that we get here, we call them as a quadrature component. They satisfy the uncertainty relation like Heisenberg uncertainty. So they can satisfy uncertainty relation like Heisenberg uncertainty principle or like position and momentum. So they have uncertainty principle like this. Now, since I'm talking about I'm talking about a light field, any light field, an electric field of light field, and now they are satisfying the uncertainty. Now, what are the uncertainty components? They are two orthogonal component of my field, and now In the uncertainty relation, you see that there's the equality sign also, right? So if I keep the noise, these are the uncertainty or noise in these two quadratures. If I keep them equal and equal to the minimum allowed, this kind of state I call coherent state, or the limit, this noise limit I call short noise limit or standard quantum limit. And an example of this is a laser beam. If you have an ideal laser beam or the most stable laser beam, then this satisfies this condition. Now, if when I said that quantum noise, I mean that the del x square or del y square is getting equal to 1 in a normalized unit. Now, the question I want to ask, or I have posed that, can I have a noise less than the laser? Or can I have a noise less than what is this limit, standard quantum limit? Yes, I can have noise in measurement of either of the quadrature less than my short noise limit, but I have to obey uncertainty relation. I have to obey uncertainty relation. That means the noise in other quadrature will be more. So if I draw this noise diagram, or we call this a phase space diagram, the noise in one quadrature is reduced, but at the expense of the noise in other quadrature, because we have to obey uncertainty relation. And in principle, you can reduce noise in any of the direction that you want. Now, if you want to use this kind of state, if you are making a measurement and then you want to get the benefit of the reduced noise, you make measurement along this direction. If you make measurement along this direction, definitely you're going to get the sensitivity beyond your classical limit or beyond your standard quantum limit. That's what we are saying, that when you have a squeeze light, you can have quantum enhanced sensitivity. So this is a motivation that I want to give you to all the students, that how I am gaining, because I have reduced noise, because this light I will be using to sense something, because it is already reduced noise. If I sense any of the parameter of my interest with this noise, I'm going to get enhanced sensitivity. So with this, what is our motivation for today's talk is, we will show that how to use this reduced noise property of quantum state of light for enhanced sensitivity. Or in particular, I'll talk about how do we generate this kind of squeeze light. Or in particular, we are generating this kind of light with a process called four-way mixing in atomic vapor. And then I'll show some of our work on the quantum enhanced sensing or quantum enhanced plasmonic sensors and parallel quantum enhanced sensors. And then at the end, I will highlight some of our theoretical work on the distributed quantum sensing that has a lot of potential for quantum networks and all. So I will, and after that, I'll finish my talk. So now coming to the introduction, what is or how do we generate squeeze light? To generate squeeze light, what we do, we use a coherent state. As I told you, coherent state is nothing but a laser beam. You can take a laser beam, and theoretically you say that you pass laser beam to some device, some black box that is called a squeezer. You pass it through a squeezer, and at the end you get it. So if you are aware of quantum mechanics, what simply we are doing, we are doing this kind of operation. The operation or quantum mechanical operation involves like this. It is, if you don't know quantum mechanics, don't worry about it. If you know the quantum mechanics, you see that it involves a square and a dagger square. They are called annihilation and creation operator. Basically, they create a pair of photon. If I have two times coming, two are coming, then I'm creating a pair of photon or annihilating a pair of photon. If any process that creates a pair of photon, in principle, that will give me squeeze light. And then the squeezing, if you look at the squeezing amount of the noise reduction, it goes like this. One quadrature noise will be reduced, other quadrature noise will be increased. Now, if the pair of photon that I'm creating, they are going along the same spatial mode, same direction, this kind of light I call single mode squeeze light. On the other hand, if I'm creating a pair of photon and I'm sending into two different spatial mode, that means two different spatial direction, then individually, if I look at those beams, they are very noisy. But on the other hand, if I combine these two beams, if I do some kind of joint measurement, then I can get the reduced noise. For example, if I look at x1 and x2 quadrature here, I can get the noise reduced in the difference quadrature. On the other hand, if I look at y1 versus y2, I can get the reduced noise in phase sum quadrature. In that way also you can get benefit by just making a joint measurement. Okay, so now having said that, our focus is mainly on this two mode squeeze states of light, which are this kind of two, we are creating a pair of photon and sending to the two different spatial direction. Okay, so then if you are interested, okay, we are creating a pair of photon, what is their distribution? Then I will tell you that if you have a one photon going this, other photon will definitely go through it, because they go through this kind of operation. A square, A dagger square means a pair of photon has to be created. So a pair of to create a pair of photon, of course, when it is created, that's a quantum mechanical process. It's completely probabilistic. But once you get one photon here, you must, or you're gonna get the another photon in the other beam. So, but when they will get, or when you will get, is uncertain, but once you get one, you will get another here also. Now if you detect these two photons or twin photon by two detectors, basically photo detector, and then you can get photocurrent fluctuation like this. Since you have photon number arriving over time is random, then you will get random current fluctuation here. But interestingly, these two are correlated, they are quantum correlated. So whatever noise you get noise of this here also. Then if you can subtract these two things, then you can get rid of this, the noise or quantum noise arriving because of the random arrival of photon, and then you get the reduced noise properties. And since you have reduced noise property, you can use for quantum sensing application. Okay, but as I told you earlier, this balance detection will lead, this kind of balance detection will lead correlated quantum noise reduction. Since we are subtracting them out, then the correlated quantum noise will be reduced. So now experimentally, how we are generating these kind of beams? To generate these kind of beams, we are using little sophisticated setup that is called a four-way mixing process in hot atoms. Basically what we are doing, we are interacting a strong laser beam with hot atomic medium, or we have rubidium atomic cell. We are interacting a laser beam to hot rubidium atomic cell, and then in this atomic medium, what happens, two photons from this strong laser beams are absorbed and two photons are emitted. And then since these two photons are emitted at the same time, we call them twin photons, or we name them as probe and conjugate, but they are twins. Twins means they are identical in all respects. If you know one, you know the other, because their propagation is governed by momentum conservation as well as energy, as well as what energy they will, or what time they will come, that is governed by energy conservation. Basically they are bounded by energy conservation, and these two beams form squeeze state, two mode squeeze state, or entangled beam. And then interestingly, what we do in our lab is we are seeding this process, we are stimulating this process by having another beam in our setup. In presence of this very weak beam that we call probe beam, this process, the photon pair generation process, gets really amplified, and then you get bright beams. You get bright beams means they are really bright. You can see quantum correlated or entangled beams of power of, let's say, 1 milliwatt. That is huge actually. So in that way, you can do many of the quantum mechanical or quantum technological aspects in the macroscopic domain. Macroscopic means in ambient light condition also you can get the quantum advantages. Now the question is, okay, we generate these kind of beams, but how do I know that these are the quantum beams? To characterize whether these are quantum beams or not, what I do, I detect these beams, as I have shown you a cartoon previously. So I detect these two beams by two photodiodes, and then look at their difference current or difference noise. And this is what we get from our system. But now to compare what is the classical limit, or what I can get, or if I do the same thing for the laser, what I do or what I do get. So this for if I do the same kind of measurement with the same power of the laser, then I get a noise limit like this. This is normalized to its mean, or it's normalized to zero. You get this is a standard quantum limit. This is a classical limit. You can't, with the classical laser, you can't go below that. But with our system, you can have reduced noise below than that. It's like we have shown, this is called squeezing. Here we have shown 87% noise reduction from the classical limit. And this noise reduction is coming from quantum correlation, because these are correlated, that is leading to squeezing or reduced noise properties. Now, of course, this is our setup at IIST, where we have generated this kind of bright twin beams, and these are the images of bright twin beams we have in our lab. And we have what I have shown, that this is what in the literature we have, or in my previous lab we have demonstrated about 9 dB of squeezing. But in IIST also we are very close to what is shown with this kind of setup. We have observed in IIST about 7 dB of the squeezing, which correspond to 80% noise reduction from the short noise limit. That is significant. On the other hand, we are generating multiple squeezer with a single cell, and then we are showing the squeeze light from the single atoms, atomic medium. We are splitting our pump or probe into multiple beams, and then generating this kind of squeeze light sources from the single atomic system, or single atomic vapor. So these are the two sources we have produced. Okay, so we have produced it. Now it's like a very natural to think that if I have a source of light that is having very less noise than the classical limit, then if I use this for any kind of optical sensing, I'm going to get benefit. That is what goes to quantum sensing. So now coming to the quantum enhanced sensing, I will tell you, in brief, what do we mean if you want to have a quantum sensing? What are the ingredients? For that, you have mainly 3 ingredients. So since you want to do quantum sensing, then you have to have a quantum source. You have to have a quantum source. You have to have a sensing device, because you want to sense something. Then what is that device? You should have that, and then you should make an appropriate measurement to achieve the sensitivity. Or I would show here, in all of the sensing, I would say 99% in sensing aspect, we don't directly sense the parameter that we don't measure the parameter that is of our interest. For example, let's say I want to sense a parameter, or I want to sense a parameter of interest P. Then it could be, let's say, pressure. You want to measure some pressure. Then what that pressure does, pressure changes some property of your sensor. That change of the property of your sensor you can detect by light. You understand? Let's say you want to measure a pressure. Pressure will change some of the property of that sensor, and then the change of the property of sensor can be probed by light again. And ultimately you see change in the light. And then by checking the change in the properties of light, you can infer what was my parameter of interest. Ultimately, you have to follow this kind of error propagation equation. The parameter of your interest is this. It changes your sensor properties M. In particular, M will change your property of light. Basically, you are monitoring the property of light, and from that, you are inferring what is the minimum change of that parameter of interest, or pressure, atmospheric pressure, for example. That's what you want to do. And if you do the simple calculation, it turns out that it's just nothing but error propagation equation. It turns out that the minimum change that you can detect, that is limited by the noise of your light itself. It could be intensity noise, it could be phase noise, or any other form of noise. That means if you can reduce this noise, then you can get minimum changes in the parameter of your interest. That's what your goal is. Okay. With this goal, I would like to show some of the work we have done when during my stay at United States. So when we were working, or we were interfacing this kind of squeeze light with some of the sensor we call plasmonic sensors. Why plasmonic sensors? Because plasmonic sensors are widely used in chemical and biological sensors. They are commercial sensors. And then another interesting thing is they have already shown to operate at the short noise limit. That means if I want to, for a given sensor, if I want to go beyond short noise limit, I have to go quantum. That was our motivation. So before that, before I talk to you about quantum enhanced, I just want to brief you what the kind of sensor we worked with. These are the plasmonic sensor, were nothing but they were nano holes. Actually, we have a glass substrate. Let's say this is a glass substrate. On top of the glass substrate, we have a 100 nanometer silver film. This is a 100 nanometer silver film, and on that silver film, we made some array of triangular holes. These are the typical sizes. And then what we found that when when any the students, I want to tell you that if you have any hole which is much smaller than the wavelength of light, or less than the half of the wavelength of light, light cannot pass through those holes. But what happens, this kind of metallic surfaces, some interesting thing happens. You pass light through them, and these are the metal surfaces, and metal is having a lot of free electrons. So you excite free electrons in those kind of triangular nano hole, and then these excitation of free electrons we call plasmons. You excite plasmons, and these plasmons, through the plasmons, your photons can pass through those holes. Basically, when you shine light converts to the plasmon can go through those holes, and then if they go to the back surface of your sensor, then they can convert back to the photon. In that way, you can have transmission through those kind of sensors, actually. And then we were probing those sensors with a quantum light of wavelength 795 nanometer, and we got about 66% transmission. Now, how these sensors sense, actually? To sense these sensors, what we do, as I said, what we are doing, we are passing light through those sensors, and then we are getting a characteristic resonance. We are getting characteristic transmission. And now, if we have a laser, or we have a given wavelength, then we have a given transmission to that. If I have a given laser, I will have a given transmission through that sensors. Now, what interesting thing happens if you change something around this sensor? If you change the pressure, if you change the refractive index, if you change anything around that sensor, what it does of its resonance, it makes shifting this resonance curve. So then if something, some parameter change around the sensor, let's say it's changed, then whole curve gets shifted. Now if you are probing this with a fixed laser beam or fixed quantum wavelength, then for that wavelength, your transmission has been changed. Your transmission has been changed. That means by monitoring the change of the transmission, you can infer that there is something has come, or some local change of the index of refraction or surrounding has happened toward my sensor. Now, the question is, when this change of the transmission through those sensors is much smaller than noise of light itself, then you will not be able to detect the smaller changes of the transmission. On the other hand, if you use the squeeze light or quantum light, then you can still detect these smaller changes, and that's what goes for quantum enhanced sensing. So that's the whole idea I have shown in this cartoon. Now, what experimentally we have done? Experimentally, as I told you, we are generating bright two-mode squeeze state of light. You can generate two more squeeze state of light, or twin beams. You send one beam through the sensor, other beam you directly send to the detector, works as a reference beam. And here you put a sensor that we call a plasmonic sensor, and that sensor we make it to sense the refractive index changes of the air. We are modulating the changes of the refractive index by changing by driving this sensor or this around the sensor area by ultrasound. We are creating ultrasound waves. These ultrasound waves are making pressure change or refractive index change around the sensor. That's what we are sensing. Okay, and then this is being sensed by one beam, other beam directly goes to detector and then used as a reference. Now when we probe these beams with a classical laser beam, if you have a laser beam and I sense with the laser beam, what I got a signal. Let's say for a very small change of the refractive index around sensor, I got a signal through that sensor. Okay, that's well and good. Now if I probe the same sensor with our twin beams or our quantum squeeze light, however, the signal height was the same, but overall noise floor is reduced because of the squeezing. Though we started with the 9 dB of the squeezing is sensitive to the losses, but still we have 4 dB of the quantum enhancement actually. So in that way, your overall noise floor is reduced and your signal height is same. That's how you are increasing your signal to noise ratio. Now, on the other hand, what happens? Now you can always argue that I was good. I got the signal. Then what is the big deal? Signal I'm getting. If I'm getting signal, I don't care what is signal to noise ratio. But you have to care when your signal is really low. When your signal is really low, or it is buried, or is equivalent to your noise, then you don't know where is my signal. But at the same time, if I probe this sensor with the twin beams or squeeze light, you can detect the smaller signal which was buried inside the noise. So that's the real quantum advantage, or that's what the power of quantum squeeze light or squeeze light here. On the other hand, of course, this is more quantification. So we looked at what is the minimum change of the refractive index you can detect with the coherent state or squeeze light, and here you see that the quantum enhancement we get is 56%, or about 56% enhancement we obtain from our experiment, which is expected as our theoretical calculation. So other than that, recently we have been continuing this kind of work, and then in this particular task, what we did, we had one sensor probed by one beam, other beam works as a reference beam, and we have shown the quantum enhancement. Now, what happens? This kind of squeeze light or the beam that we are generating, they are multimode squeezed. What we mean by multimode squeeze state? So they can have, if you take a snapshot, if you take image of those beams, their different points are correlated different. This point is correlated to this point is correlated to this point. There are different channels or correlated channels. That means if I use only one beam to sense the multiple sensor, can I get the quantum advantage? That's what we have tried to look at in this ACS photonics paper, where we have integrated this kind of beams with the parallel quantum enhanced or parallel quantum sensors. So the idea is, in the previous one, there was only one sensor sitting here. Here, instead of one sensor, there are quadrant of sensor. There are 4 sensors sitting there, and then we are making 4 detection. Ultimately, we are sensing the signal coming from individual detectors, and then for that we have used the quadrant detector, as you can see here. And then as a result, what we have shown here, these are the results. So with all the 4 sensors probed by one beam itself, you can have, or you can see a signal that was buried. You can see signal with the squeeze light that was buried if you have done that with the coherent state of light. With the classical state of light, you can't detect that was buried inside this black trace you can see here. But with the quantum light or squeeze light, you can still enhance that. That was a very significant work to make parallel quantum enhanced sensor, multiple sensor sensed by a single beam. Now, okay, this is for the one kind of sensor that is called plasmonic sensors, where that these two works are done in collaboration with the University of Oklahoma as well as Oak Ridge National Lab in United States. So now, what here I will show you like in next 5 to 10 minutes, because after that I'll finish my talk. I'll talk about some of the very recent work that we are doing on quantum sensing aspects. That is, we are not only just looking at single sensor, we are looking at distributed quantum sensor. In particular, what we are interested on gyroscopes. If you are interested, you can look at this work. Of course, this is again, this is a theoretical work and then done with Professor G.S. Agrawal of University of Texas and A&M. So in this work, what we have shown, we have a gyroscope or a network of gyroscope, and they are probed by the bright two-mode squeeze light we generate in the lab. And then whether we can get quantum advantages or not, this kind of work we have done. So just again, I would like to introduce you how a gyroscope works and what do we mean or why do we care about this work. So if you talk about gyroscope, gyroscopes are everywhere. Gyroscopes are rotation sensors. Rotation sensor, or they will tell you direction. They can tell you direction. They are your orientation sensors. If you talk about gyroscope, where are used? They are used everywhere. For example, spacecraft. In any, if you are going from through aeroplane from here to United States or here to Delhi, then of course you have to have a gyroscope which will sense which direction you have to go. On the other hand, if you want to look at space application, let's say you want to land on the moon, then how do I go from here to moon? I have to properly there has to be a system that will guide me which direction my spacecraft has to go. That is done by gyroscopes again. So gyroscopes are everywhere in most of the advanced technologies. And then how in principle gyroscope work? So gyroscope, most of the gyroscope, they are working in the principle of Sagnac effect. In that, what is done? You send a laser beam to a loop of a interferometer, a fiber loop. You send a laser beam to a beam splitter, split into two parts. Some part goes here, some part goes here, and then you make it a loop. You send it through a loop. Then what happens? Since they are in a loop, so the beam that goes in this direction or that direction, they travel equal path. When they meet here and they interfere, they meet equal path. But what happens, interestingly, if you rotate this device, if you rotate, or if this device rotates or inclines, then what happens? The beams that are traveling in these two clockwise and as well as counterclockwise paths, they get a phase shift. And that phase shift is given by this. That they get a phase shift that is given by this. And this phase shift depends on your angular velocity. What velocity it is rotating, or what is the orientation of that, it depends on that. So just by measuring what is the phase shift your interferometer is having, then you can infer what is the angular velocity, or what is the inclination or angle of inclination of your device or your whatever spacecraft or whatever you want to use it for navigation purpose. So in this work, what we have proposed a sensor or network of this kind of sensors, and these sensors are probed by the two-mode squeeze state we generate. We generate two-mode squeeze state, and then out of two-mode squeeze state, we generate multi-mode by passing through something we call symmetric beam splitter network. And then ultimately we are sensing the phase shift by the multiple sensors, which are network of sensors. And then we have done joint quadrature measurement, and then from there we are inferring what the sensitivity we can achieve. And then our results show that we can really, this was our classical limit, short noise limit. This was our classical limit. And then for our configuration, we can beat again classical limit. And then interestingly, our classical limit, or the way that the system that we have, it can go to the ultimate limit also. that limit is characterized by something called quantum Cramer-Rao bound. This can go to ultimate limit. So in principle, I will not go to too technical. In principle, if you make a network of gyroscope like this, then you can have ultimate quantum enhanced sensitivity that has a lot of technological aspect, because I had already told, gyroscopes are everywhere. So with this, I would like to conclude my talk. What I discussed in last 40 to 50 minutes is, we talked about squeeze light. We talked about how do we, or what are the reduced noise properties of squeeze light, how they can be useful for quantum enhanced sensing application. In particular, we focused on squeeze light generation with a four-way mixing process. I must tell you that this is the process that we are using, but there are other processes, nonlinear processes people use to generate squeeze light also, that I could not cover it today. And of course, we have shown that these kind of squeeze light can be interfaced with the commercial sensors and then can show the enhancement in the sensitivity. And at the same time, I have presented a network of gyroscopes that can also get the benefit of this squeeze light. With this, yeah, definitely I would like to acknowledge the people who are behind the work. So this is the team I have in IIST. These are my PhD students, and these are the some PA master students who just passed out, or are continuing. Of course, I'm collaborating with Professor G.S. Agrawal for Texas A&M, and Professor Alberto Marino was in the University of Oklahoma, now moved to Oak Ridge National Lab, is my long-standing collaborator. And then, of course, Rafael and Benjamin, we collaborated for this plasmonic sensor work. So with this, I would like to thank you all. And then if there are questions, I would be happy to take.